After Harry come Tunguska, so we have here Bo Lund Rasmussen from Odense, and he's going to explain us about the carbon compounds on the Tunguska compound.
Yeah, yeah. So, it would be nice when we're talking about biochemicals that we could actually lay hands on them. So the sample return mission to wild is one way of doing it, and I'm suggesting to you another way of possibly doing it. In 1908, at 14 minutes past 7 in the morning, just when you had your morning coffee, there was an impact in Siberia. The impact exploded at 8 kilometers height and released an energy of about 12.5 megatons TNT. And the impact of mass was about 1 million tons, and the impact of velocity was, with the uncertainty that these calculations now possess, is about 40 kilometers per second. That could easily be 20 kilometers per second, but it could not be much more than 50 kilometers per second. The forest area destroyed was about 2,000 square kilometers, and many eyewitnesses' accounts from Russia and Europe have been collected. There was an unusual bright night the night before the impact. This is a bit strange, not after the impact, before the impact. And many people interpret that as evidence that it was a cometary type impactor, and that the tail impacted Earth 24 hours before the main body.
Clear night, you say?
Yeah, very clear night.
But what does a clear night have to do with bright?
Bright light.
Bright night.
Bright light.
Right.
Yeah.
Yes. Okay.
Not dark.
So some glow or what?
Yeah.
Yeah, glow. People could read a newspaper at 12 o'clock at night.
Yes.
That was unusual.
Yes.
The impact site was first visited 19 years after because of the turbulent history of Russia at that time, and there has never been recovered any substantial extraterrestrial matter, but unsubstantial perhaps. This is a picture that was discovered, at least by the scientific world, only 1 year ago. This is doctors and monks from the monastery in Aalborg, and that was the night before the impact. They were having a dinner party, and it wouldn't become dark. And so they went out at 12 o'clock at night and had their picture taken in the garden without any artificial light. That's really a very good proof of there was something in the outer atmosphere.
So this is what you know that for sure?
Yeah.
Okay.
Yeah.
So what's the reference in this?
What?
There's a reference in this?
Oh yeah. This fourth man here is Anders Kind. He was an eye surgeon. Is that the right word?
Yeah.
Yeah. And his grandson has given me access to this picture. Yeah.
So you said that this picture is taken in Denmark?
It's taken in Denmark, in Aalborg, in a meter cluster in Aalborg, the night before the impact.
It was in Scandinavia you had the bright lights. Okay.
From the Black Sea and Eastern Europe up from Scandinavia to Christiania in Norway. And there's many pictures, you know, where you just see some white blush. I mean, that could be anything, right? This is actually people who see their. I think it's
you know, in Shell you had the heat coming as well.
The heat?
Yeah, so it's in the goldsmith 24 hours before the comet tonight.
But in Russia it was more severe. This is taken in 1927, and you see the devastated forest area. And here it is in 1931. You still see the big trees. About 100-year-old trees were turned over for an area of 2,000 square kilometers. It's an interesting area. In the lowlands, it's tundra, and on the highs, it's just a normal forest area. And this is on the Danish-Russian expedition in 1994. You can still see the big tree trunks lying there now, obviously 100 years after the big trees that is grown out.
This is a 100-year-old tree, that's not decomposed?
very close to the tongue box.
Oh,
There's nothing going on up here, it's almost dead.
Yeah, very well preserved. Everything there. The implication is that it's probably a cometary type impact, and it's very certain that there was a stratospheric ejection, and thus a worldwide distribution of impacted material, because the explosion took place in 8 kilometers, 8.5 kilometers is the best estimate, and we are 60 degrees north, so we're close to the tropopause. It's around 7-8 kilometers at the polar regions. And when you detonate 12 megatons of TNT, you certainly will inject some material into the stratosphere. So we should have a worldwide distribution of this extraterrestrial material. But unfortunately, there's no iridium seen in Greenland or Antarctica. I'll show you the data for Greenland here. This is iridium 10 to the power minus 15 grams per square centimeter per year. And you have the years from 1905 to 15, and you can see 1908. There's no significant rise there. In 1909, it's just like 12 or 13. There's no really big difference. This is recovered from an ice core by the geophysical department here at University of Copenhagen, kaare site B, which is indicated here on the map here. And you have here the delta C, delta O18 curve, and you can see we very clearly mark the winters and get the ice out. We have the asterisk here, 1912, indicates volcanic eruption in Alaska, Katmai in 1912, and that fits with the suffering there. So we're very, very sure of the date of this event in the ice core. And we're also very sure that we do see extraterrestrial material in the ice, in the dust of the ice. And what we did was we took the ice, cleaned it, melted it, extracted the dust, neutron activated the dust in order to find the iridium. And you can see here that the circles are kaare site B, and the squares are CI contracts. And it's normalized to crust and samarium. So this here one is crust and samarium normalized. So it's very close to Earth conditions. But when you come over to these elements, the stereophiles, you see the TI goes up here, and also the ice is very significantly raised over this curve. So it's about 1 per mil of extraterrestrial material in the ice. These samples are from 1904 to 1915 averaged. So this just shows that we can see, we're sensitive enough to see the extraterrestrial material in the ice, but there is no iridium in the ice. A French group has done the same thing in Antarctica and didn't find any iridium there either. And this sort of moves to what I'm going my point today, namely that do we really know what the chemistry of the comet is? I mean, we assume if you look at books and the literature, at least the normal model is perhaps 50% volatiles and 50% CI. And then when the comet comes in and it takes several passages around the sun, obviously the volatile will go down, and the CI should be very dominant. So it's a bit of a problem. We should be able to see the iridium. 1994, we covered 4 drill cores and sampling precision 5 kilometers from the epicenter. And the cores were around 100 centimeters long, and they penetrated into the 16th century or something like that. We measured iridium by INNA, and C14 and C13 was measured in 5 centimeter core slices. That is neutron activation analysis. This is a map of the areas 4 kilometers scale bar here. Quick scan, that was the guy who were there in 1927. It was a Danish scan that was the same example. And this is the data from the peak core. On this scale here, you have the iridium in picograms per gram dry peak, and that's the green curve, so you can see very clearly. We have the impact probably center around here. And this curve here is the C14 measurements. And what you see here is a pronounced drop in C14 here. This is the expected curve of C14. Obviously, as you go down in the core, you get less and less C14 because it will decay. But what you see here is a drop and then a return to the original curve. So this yellow area here is our interpretation of the amount of extraterrestrial carbon deposited there. You get my point? The extraterrestrial carbon is free, is void from C14, whereas the normal deposition in the peat core will have normal high threshold 100% radiocarbon in it. So when you see a decrease in C14, it comes from some other source, and when we send it just exactly around the extraterrestrial peak here, it's obvious to interpret it that way.
That's because carbon 13 is enhanced, or what? That's because carbon 13 is enhanced?
Because carbon 14 comes.
Carbon 14 is
But now what?
decreased.
But that's just a relative. So
Yeah.
is it the carbon 14 which is absolute units also decreased, or is it carbon 13 which is increased? That's the relative.
Carbon 13 is carbon 12 and 13.
12.
Yeah, 12. Oh, even 12.
Yeah.
Do I understand correctly that you are saying that you have kind of several centimeters of extraterrestrial carbon in the peat at this moment?
Yeah, I mean, what I'm saying is that the extraterrestrial material is spread over a certain depth in the core. And that's because when you have a peat surface, if you imagine 1908 and you have this peat surface, and you deposit some material there, it's very, very fluffy. And so a little bit of rain and just percolation of you will bring the material somewhat down the core. Then you deposit new peat on top, and then it sort of the compaction takes place just like ice.
But can you estimate the total amount of how many kilograms per square meter of extraterrestrial?
And that's my next slide. I'm going to show it says that there were some questions here. I mean, this is the crucial point of what I'm talking about.
Okay, so let me just ask you a stupid question here. So why don't we see any carbon 14 in on the asteroids, on the comets?
Because they are 4.5 billion years old.
Because they're continuous with using that,
Yeah.
because with radiation.
Precisely.
I guess because there is no nitrogen in the comet.
There's what?
There is no nitrogen in the comet, I guess. Because that's where the C14 is.
Yeah, I mean, there will be a little bit of radiocarbon in the comet because of radiation onto the comet surface. But that would be very tiny.
Okay, so this is an established fact that we know that there's no carbon 14 on the...
In these rights, yes.
Okay.
That's the way that, for example, the Alan Hills 84001, one of the arguments against that was life. Old life was that they had carbon. He was 12,000 years old. It's very bad if it was supposed to be life of 4.5 billion years old. That was one of the points. Yeah.
Have you thought about taking a comparison sample from the area of the tundra which has not been affected by the cometary impact?
That would be nice, obviously. But the fact that we find the video is very, that's very unusual. The Cretaceous Tertiary boundary, geochemists have been looking all over the world for a video. I mean, it's a very established research field. That once you find a video, you definitely have some impact material. And one sample might be a little shaky, but many of the Cretaceous Tertiary impact events, sites that have been established, is established only on one sample. But here we have 4 samples.
Maybe you should spend 1 minute on just explaining to people why there's no region on Earth, but there are in meteorites.
Yeah.
Would
that be, Earth's surface is 10 to the 4 low in iridium because when the Earth was young, that was the normal solar system abundance of iridium on Earth. But the formation of the Earth core sucked up all the iridium because iridium is very stereophile, went into the core and is sitting in there in the core now. But the surface of the Earth is depleted in iridium relative to meteorites, to CI, to chondrites, CM, by a factor of 10,000. That's why we can so easily find cosmic material on Earth just by analyzing for iridium.
And the iridium due to cometary impacts is rather spread away in the Earth's surface, right? Or is it localized?
It's localized. When you have impact, you find it, for instance, at the Cretaceous Tertiary, that was a very big asteroid, like 5 to 10 kilometers, and that spread worldwide. You had ballistic ejection, and then it fell down again. So you find the impact took place in the Yucatan Peninsula, but you find iridium in China, you find iridium in Denmark, you find iridium in Italy, and so on. So that was a worldwide today.
Okay,
But normally you just have an ellipse
Yes,
over the surface of the Earth.
yes.
That's the normal way.
It's a smaller.
Yeah. Depends on the energy available.
Just another, would you say sort of the expected decay, is that sort of based on theory, or is it just a continuation of these 4 points?
That's a good point, very good point. And we were criticized in the literature for this. But the fact is that you can see that this curve goes up here. And up here at 150%, we have the next 3 points. Those 3 points are bomb-induced radiocarbon from the bomb test in the 1950s and 60s. So it comes down to 100%, and it's a little bit over 100%. You see, it's 102. And that's because you have some mixing of the very high radiocarbon level from up there. The point is that this is a centimeter scale, so we don't really have the possibility of dating it. Once we get down here to 90 centimeters, we have a date, real date, we can get a real date. The radiocarbon age scale does not work between 1620 and 1950. So we have a 300-year blank period we cannot date.
Wow.
Because the radiation from the sun has varied so that the radiocarbon production in the atmosphere was raised during that time, which means that you get a blindness over there. And when you look back in history, the past 10,000 years, you see various periods of blind, where you have higher production of carbon-14 in the atmosphere, and therefore you cannot date. Unfortunately, this is one of them.
But, I mean,
So that
means
means
it might be non-uniform, but they're sort of considered time, because otherwise, of course, Green Peak there, you have to date for that, if you assume that was the comment.
that was 1908, yeah. But still, again, you have a problem here because if you follow my idea that the surface is very fluffy and you salt the surface and you percolate the material somewhat down to the core, what you really should see perhaps is that this is 1908, right? And then it percolates downwards. But that would go for the carbon too. And you see definitely that this sample here is affected somewhat by percolation from the 150% rate of carbon back. So there is a percolation effect. Therefore, when I don't know the precise age versus depth scale here, normally you have in these sediments you have compaction. Therefore, you have an algorithmic depth scale. And when I don't know that, I cannot put precisely say that this is 1890, for instance, and therefore I know the rate of carbon production that year. So this curve is tentative, and we can try to within a factor of maybe 2 or 5, or 5 I think is low, 2 or 3. There could be a factor of 2 or 3 uncertainty in this. My point here is now, if we integrate this peak here, and we integrate this yellow area, then we can calculate the carbon to iridium ratio for the impact. And that would be the first time that was the first time in literature we've got the chemical signature of the carbon. That's what oh yeah. Another point is that we have measured the delta C13 of the samples, and usually it's minus 25 per mil ppb. But as you go deeper and deeper, the core decomposes, and it's very normal that we go down to maybe 25.5 per mil because the peat is decomposed a little bit. That's very usual. But as you can see here, the same interval, you have drastic over 1 per mil increase in the delta C13. And the difference here between that level and this level allows us to calculate the delta C13 of the impact material.
What does it mean? Is it PDB? PDB, what is that?
PD benamites. PD is a location in the United States, and benamites is an animal. So they're taking a lot of things in the animal. It's standard, it's standard.
But what is on the axis there? Did you explain that? The minus 25, what is that?
That is delta C13. That's the delta C13 compared to the normal standard. It's actually the NPD.
I still don't understand what the PDB is.
That's the standard.
But of what?
Of 100 million year old marine animals. That's the wet standard of density 13.
Okay, all right.
Okay, so if you take a marine sample, it will be 0. If you take a terrestrial sample, it will be minus 25.
See, there's a standard for water. Which is something, go receive water from somewhere, something more,
Yeah, yes.
to make sure you have the isotopic ratio.
Okay, good.
And all terrestrial material, all plant material, all animals that eat terrestrial material will be around minus 25. When you go back 60 million years, you have changed 1 million. It's very, you can see we hit it, but it's very close to minus 25.
It's a very important argument to tell whether something is biological or not.
Yeah.
If you look the difference between material and what you find, you can go out and detect biological processes that are present or not without having an animal or a plant or whatever, just by looking at these values.
Precisely.
To return to Mars Mitra, it was one of the arguments for why the fossils they found were from Mars, was because they had this depletion. And by that they are indicating that you have photosynthesis life on Mars, which because it's due to photosynthesis that you form this depletion, as far as I'm still right.
Yes.
So,
In biology, we also use it to point on specific processes for the fixation of carbon.
That's
Because
correct.
they give you these delta C, this is 13 values, which are specific for
precisely.
for process.
The interesting thing here is that from this difference to this difference, I can calculate the density 13 of the impact of material in the Tunguska. And it's written here. First, we have the carbon to radium atomic ratio. That's 1.2 times 10 to the power 9, which is extremely high carbon and very low radium. Contracts, for instance, have a carbon to radium ratio of only 10 to the 5th approximately, at least a factor of 10,000 less than we find.
Do you know that contracts are not old comets?
What?
You know for a fact that contracts are not old comets?
Well, I mean, this is what I'm coming at. If you just allow me a little bit of discussion. See, the delta C13 is calculated to be plus 55 per mil ppb. Carbonaceous contracts are in the range from plus 40 to plus 60. And egg contracts are from minus 30 to minus 20. That certainly doesn't fit very well.
you should probably say egg chondrites have been parts of planetary bodies.
Yeah, egg chondrites are from asteroids that have undergone thermal development. Ordinary chondrites, which are chondrites that has also undergone some thermal processing, are from minus 60 to minus 10 per year. Carbonaceous chondrites are the primitive material in the solar system. And so it fits very, very well with the hypothesis of that it's a CI material in the impact. But this up here certainly raises a point if we know, if our models of comets are really correct, or maybe the Tunguska impactor was some special beast in the solar system that we just haven't laid hand or eyes on before. That's another possibility. Either it's a very special beast and we have a very special access to cosmic carbon here, or comets or models of comets are not what we think they are.
Does it see C2013 being recently in the spectrum from a comet, or is that known in comets?
I don't think it's only for comets.
So,
about to my knowledge.
So how does the carbon composition compare with other carbonaceous chondrites?
Very well. Plus 40 to plus 60 is the results of these guys, and we get plus 55.
Yeah, what about okay?
So that's the carbonized top composition. That's primitive solar system composition, all right. But what is not normal is this very, very high ratio we have. So it means that
No, but wait a minute. In the carbonaceous chondrites
Yeah.
that we have the megatons. What is the thing that we have investigated? Does it also have a much higher uranium content than this one?
yes, that would compare to that.
And there was an impact up from up in snow in Canada recently.
Turkish lake.
Yeah.
The meteorites for Turkish lake.
Yeah, Turkish lake. Does it also does it seem to be such fluffy stuff that it was also very difficult to detect? We had a lot.
I haven't seen analysis of that. I don't know about that one.
Do you know that?
Well, the only thing I know is they didn't find any amino acids in it, which was really surprising considering they found it in merchants. I don't remember the reading content.
This is
But it is different, in a different way. Because
Yeah.
it was already carbon.
Yeah.
The point here is that if you calculate, now I've just written the carbon to a radium ratio, but if you try to calculate the total carbon in the impact, it will also be quite high, but not unexpectedly high. It will be something like 10 or 15% of the impact on mass that will be carbon. What's really unusual here is that the radium is so low, and that means that the content of normal CI material is very low.
How do you know the total mass?
The total mass, well, I know the energy, because that was recorded on seismic equipment all over Russia and Europe. So I have the total energy. That means I have half mv squared. I have a very good estimate, within a factor of 2, very good estimate of the velocity, so I can calculate the mass.
But doesn't it depend on what you're shooting for the density?
No.
No. But where do you have this estimate of the velocity?
Of the velocity, we have more than 5,000 eyewitnesses accounts. And it came over China, over Lake Baikal. It was first seen over Lake Baikal, and then we have eyewitnesses accounts all the way. Obviously, it's very difficult to estimate how many seconds such an event takes. We also have some seismic station also gave the momentum. The first movement of the seismometer gave the momentum somehow. When you couple that to models, plus that you have the total energy. I mean, obviously, let's say that the mass, it lies between 1 million tons and 10 million tons. That would be a good range.
But can't you also see that? I mean, I've seen calculations where they tried with various parameters, the mass and the velocity, could have a pretty good pattern on how the trees were fell, and then they did, they had different angles and velocities and masses. So
one of the famous model calculations has been done with Alaska. Days of old in the 1960s, they took a hand grenade and they put a little mastic up.
Yeah, they were rolling it in on a string.
Yes, and the explosion there, and they simulated it is very famous fall patterns of the trees that's called the butterfly pattern. So it looks like a butterfly, the fall pattern, with a symmetry axis on the flight path in towards the explosion.
But that also narrows the inclination angle and velocity pretty much, doesn't it?
Yeah.
Because if you
The
a small window, which
that's very true. Yeah, very small window. The angle was about, I think, 15 degrees between the ground and velocity.
The altitude? How to get the altitude?
No, the altitude. I would say obviously.
So the seismic, I mean, if you want to calculate the energy from the seismic measures, you need the altitude of it.
I don't think so.
Oh, because you assume half it goes down.
Yes, something like that.
What is the conductivity range for the Earth? For terrestrial material?
The surface?
On the surface, yes.
For terrestrial material?
Yes, conductivity. You think it's 10
that would be very, very high.
higher than this 10 to 9?
Yeah.
Okay.
Yeah. Because the rhythm is just below the taxi limit. And we are talking less than, probably, certainly less than kilograms, but probably less than femtograms. Yeah.
Coming back to the total mass of the impact, couldn't you get an estimate at least one of the amount of carbon and really of the total mass?
Yeah.
From your measurement?
Yes.
I mean, you have only cause something of the site.
Yeah.
Is it
Yes,
consistent
on that
with the
calculation.
seismic
Yeah.
estimate?
It's about 15% of the impact mass is carbon.
Yeah, but we know in absolute terms, you know the amount of grams of C12 per gram of your sample. You know the surface over which this is spread out, you should get also an absolute amount of carbon.
We obviously only have one core at the center. But if we assume that the material was distributed over an area of 2,000 square kilometers, which is the area of density forest, we think it's exactly with 1 million tons. But obviously there's a distribution there. It's not so simple.
Of course.
Yeah.
So I wonder what is
Yes.
Oh,
Yeah, certainly. I will finish up.
No, because you want.
The conclusion is that we have very low radiant impact, unexpectedly low radiant. Very high but not unexpectedly high levels of carbon in the impact. And therefore, we have a high actual biological potential here. We have primitive density 13 signature, the physically CI contrast, and we have a so far unknown parent bond. Or if it is known, then we know that our models of comets are not right. Yeah.
Primitive C13 signature, so that's there's nothing living in the carbon from
No.
the comet?
That's my feeling. But I mean, that would be very interesting too. I would be very happy to run the expedition and get some material back and some biologists will have a look at the material. Obviously. That would be fun. Very much fun.
Well, isn't that fantasy that life should be in comets? That really to be taken serious? The seeding type of ideas?
You will hear
It's
about
always
that
seemed
point of,
ridiculous to me.
yeah, but you'll hear about it at point of the assortment.
Oh yeah, okay. I should.
I mean, considering that delta C13 is plus 55, I would also say that it looks like there's been no biological activity on that one. But that's just a physicist's point of view.
Anyway, should we? It's great. I mean, it's almost impossible to distinguish between the question session and the presentation session. But you said that things are working here. There was a couple of people I cut off. I mean, you can say anything.
No, I just give an estimate of the content of the impact. The composition, the other composition other than carbon and iridium.
Yeah, there's a Hong Kong group that has measured that recently, and they have measured most of the noble metals. And it's sort of the way I read the two papers. It is kind of called how HOU. The noble metal concept, I think, is significant. I think they're just undistinguishable. I mean, they can't distinguish when you look at other elements like rare earth or strontium.
Is there more or less of noble metals?
There's more.
So you have to go out and pick for gold.
It's still a very low level. It's an extremely low level of
What's the reference? What's the reference to the Earth crust?
Solar
composition?
The guy,
No, not reference to the paper, the reference to the measurement.
Which can relate the abundances.
Is the
always to CI. That's our sort of standard.
Okay,
Yeah, combinations complex of CI in Buddha type class. That's all the.
This is probably a big snowball then. So water has been the major part of it.
Could be, or CO2.
CO2. If it was water, would you imagine that you could find some of that? I mean,
wouldn't that just evaporate? Yeah. Wouldn't that just evaporate?
Well, I guess.
You have a hell of a lot of water. I mean,
it would be so. I mean, yeah, it would just go. There's no watering these low plants or anything like that.
But there are these. There's this. I mean, there have been historical records of meteorite falls where they find some. There's a famous one where they. Where ice comes down on the earth and they put it into a water stable. They fill it up with all that material, and the day after, 2 days after, it's all gone. But that doesn't prove whether it's water or CO2 or whatever it is, methane. But there has been historical records of volatiles. I think it was in France.
So basically, you're saying that the energy, the kinetic energy, could be contributed differently than just evaporating the whole thing.
Yeah.
So you only have a thin shell of some black.
Well, the point is that normally, when you look at a crater like the Arizona crater, that was caused by an iron meteorite. An iron meteorite is so ductile that it won't break up in the atmosphere. You burn off some tiny part of it, and then it will impact, and you have a huge crater, okay? And you go out, if you walk a few miles away from the Arizona crater, even today, you can pick up pieces of meteorite if you're on water. It is possible. On the other hand, if you look at the chondrites, if you look at the stony meteorites, the largest stony meteorites that has survived on Earth is Yilin, the Chinese meteorite, which is 1 meter across, about 1 ton. And that shows that the stony meteorites break up in the atmosphere. But here you have something that doesn't even make it to the surface. It explodes and goes to nothing at 8 kilometers height. To me, that sort of proves that, and you have no crater, it's a Huasca. And they have been looking desperately. Of course, Kulik in 1927, he thought it was meteorite. He was digging in the ground and
you
didn't
see
find
the whole lake, because it shows on the bottom of the lake.
Yeah, I mean, he kept looking for all his life. He was killed in 1944 in the East Front, the Germans. But until then, he was in Tunguska like 8 times, and he kept looking for this. He thought there must be a meteorite. He didn't find it. Combined with the fact that it exploded 8 kilometers high, shows to me that it must be very, very fluffy, very, very easy to break up.
Okay, there's something that I've always been wondering about. Why don't we see more carbon on Earth? If we look at the abundances on these bodies that hit us, how come we have so little carbon?
They have a lot of carbon. All the damn trees.
No, but if you look at the whole crust, the composition of the crust lacks a lot, and we compare to.
You have huge amounts of carbonate rock.
Yeah, but not nearly as much as you would have
if you took all the carbonate rocks on Earth and converted that into CO2, you have 60 atmospheres of CO2 pressure.
No, but this is not. If you compare with several percent of carbon in
each rise.
Yeah, and then you compare that with what we have in the crust.
I mean, why particularly crust?
Oh, well, I don't know. I mean,
Is it the mantle or the whole Earth? You think?
The carbon is pretty light.
Yeah, but we could lose it from Earth. Is that your point?
No, no, I don't know where it is, but if you take the geology books and you look at the abundances of carbon is a light material compared with silicates and all the other materials. Then you find that they're not like what we find in these bodies that hit us and what we see in some of these clouds, but certainly that there's much less of carbon. And I don't know. Some of the theories are that it is somehow gotten captured and it's deep down so we can't see it.
That's one possibility.
Yeah, that's one. But I don't know. This is just I'm wondering because I'm interested in carbon. But what do you think of it?
I mean, I think if you consider how the Earth formed, the Earth was put together and it was very warm in the beginning. We had a runaway core formation that heated the Earth very, very much. So you had a very hot initial Earth, and you would lose an enormous amount to space.
Mm-hmm. And that is enough to account for why we have so much oxygen. I mean, oxygen isn't disappearing as much.
Well, we have a lot of carbon too. As I say, in the carbonate rocks, if you convert that to CO2, you have 60 atmospheres of pressure.
Yeah, but that's not very impressive. Well, I don't. Who has?
If I may interrupt into this discussion, I think one has to consider a little bit what did the solar nebula look like at the time when these things condensed out. So if you go out to the very far end of the solar nebula where the comets form, a lot of the carbon will have been in CH4, and
yes,
it will not condense at the Earth's region. So you lose a lot of carbon that was in the form of gaseous CH4, and then you will have a lot of carbon that was bound in CO, which you would also lose. And if you compare the carbonaceous chondrite with the solar photosphere, then you will see that both carbon, nitrogen, and oxygen is down in carbonaceous chondrites compared to the solar atmosphere, compared to other elements up to silicon. So you probably even the carbonaceous chondrite, I mean, even though they're called carbonaceous, they're also depleted in carbon. And the Earth will be depleted more just from the temperature of the solar module.
So the carbon is there is a I don't know, but what you're saying is that the carbon will go up to the fringes of the.
No, I say that only at the very edge of the solar system, where the temperature was below the condensation temperature of the nebula, you have all the carbon in the nebula condensing into solid form, and therefore be included in comets or whatsoever formed out there. But in the inner region, you have a huge amount of carbon bound in gaseous molecules that condense at very low temperatures, so they never be included in the Earth, but they will fall on the sun or they will be blown out of the solar system or whatever happens to the gaseous nebula. So therefore we should expect a depletion of carbon and oxygen, and mostly of carbon. Go back to silicon or whatever you may like.
Yeah, because the oxygen would make compounds with silicon that would keep the oxygen in the inner solar system at that time.
Okay. Thank you.
What about other impacts that are really the cometary impacts? First of all, how many are there? Other cometary impacts? Any?
I don't think so.
So that's the only one.
Yeah. Yeah.
I heard about this impact in September 2002 that also seems to have exploded at higher altitudes. Have you heard anything about this?
I mean,
No, not really. No.
I I mean, there is some satellite observations by the Americans on light type things, and seemingly they see a lot of impact on the Earth's surface that we don't normally record. I mean, several a year.
Isn't it something like 5 per day?
Something like that.
I mean,
Or maybe some more.
Could you show the second last slide? Oh. I mean, the question is about the delta C13 of non-primitive matter in the solar system. So it is lower than next one. That one is. I mean, this HED, for instance, it's minus 30 to minus 20.
Yeah.
Why is that? What process diminish 13?
That is process chondrites.
Yeah.
Okay, let's start with the chondrite. Silicates and iron nickel metal mixed together, finely mixed together. The chondrites are really like lavas or terrestrial plutonic rocks that is where there's very little metal in it. So the achondrites have formed on a planetary body where you have geology.
Is this delta C13, is it the absolute abundance of C13 relative to the mass of the system, or relative to C12?
This is relative to C12.
Okay. But I still didn't understand how the isotope composition can change. But I still didn't understand. I mean, what processes are working out there to change this isotope composition? I mean, why it is different for ordinary chondrites and achondrites and this?
That's strange. That depends which achondrites and which ordinary chondrites they have looked at. The ordinary chondrites are from a parent body. Most of them, they're from 3 different parent bodies. And they have been heated, but not to the point where you have core formation. So the ordinary chondrites have been heated somewhat, maybe to 700 degrees or 800 degrees, but not to the point where you get the metal to melt and go down and form core.
But why does it change the isotope ratio?
Well, I mean, I'm not God, I don't know. But I mean, it's some processes where you have fractionation. Obviously. You get some chemical analysis. Every time you have fractionation, the fractionation process, distillation, condensation, dissolution, you will have a shift in isotope ratio.
I've been wrong in this meeting before, so I might be completely wrong, but isn't it because, I mean, it's heated, and then the tars you have go into combination with some of the oxides you have, and then you form carbon monoxide, which simply
Evaporate.
evaporates.
That's fractionation. There are a multitude of processes that would give isotopic fractionation. Yeah.
But wouldn't that process deplete the lighter component relative to the heavier one?
Yeah, I don't know, because I still don't understand why photosynthesis prefer carbon 13 to carbon 12, or is it the other way around, whichever. So apparently there is something with carbon 12 and 13 which they behave.
It's the other way around.
It's the other way around. Okay.
So I have a suggestion. So now we have about 15, 20 minutes or something left. Move the discussion up to the morning session, so it is our current speaker and the 2 other speakers, so we could have a. And one way to do that, I mean, we had just to remind you, we had a discussion